Hello everyone. I hope you all of you can hear me and I'm audible. So let's start today's discussion session. Today again I will be discussing a few problems from this course. Today's aim is to discuss a few problem on Riemannian integral, and we will also discuss a few problems from differentiations. Okay, so let's start today's discussion. Um, yeah. So today I will be Yes, so today I will be talking about questions. I will talking about questions on Riemann integral and differentiations. Okay, partial differentiation, directional derivatives of function of two variables. Okay, so we will start with questions on differentiation and then we will move on to discuss questions on Riemann integral. We will see some properties in those questions of Riemann integration. So let's start today's discussion. So, so myself, Prerak, and I conduct these live discussion with you guys to discuss questions, to show you how to solve question exercises from assignment. Okay. This is another one of such session. This will be of 2 hours long, and recording of these sessions will be available on my YouTube channel, which is named as Maths with Prerak. Okay. Okay. So let's start today's discussion. So question number one. So in this question number one, we have a function from R to R, and you fix a point x naught in R. Then for every point, then for every m in R, then for every m in R, we define a function am, which is again a function from R to R. Okay, and the definition of this function am is given in such a way. Okay, so this is the definition given. Fine. Um, so now you need to find out which of the following statements are true. So first statement is AM is continuous at x naught for some m in R, then f is differentiable at x naught, but the converse is not true. That's the first option. Second option is f is differentiable at x naught, then AM is continuous at x naught for some m in R, but not converse. Okay. Third option is f is differentiable at x naught if and only if AM is continuous at x naught for all m in R. And D option is f is differentiable at x naught if and only if AM is continuous at x naught for some m in R. So first we will try to understand this function, okay, and then uh, we will check continuity of AM at x naught, okay, for some m in R, and then first we will assume that f AM is continuous at x naught for some m in R. Then we will try to prove is it differentiable, is f differentiable at x naught, okay, and then we assume that f is differentiable at x naught. Then does it imply that AM is continuous for some m? And then we will try to prove that. Can you give me an can we consider an example of AM for some m such that this equivalence doesn't hold? Okay, just give me a minute. Okay, give me a minute. Okay, so in this question, okay, so I hope you can hear me. Uh, so first we will try to prove. We will assume that AM is continuous at x naught for some m in R, and then we will try to prove f is differentiable at x naught. Okay, so let's start with the definition of AM. So AM is a function from of a real value of a real variable and gives you a real value, and it is defined as AM of x is equal to fx minus fx naught minus m times x minus x naught. This whole value is divided by x minus x naught. Okay, so if you simplify this expression can be simplified to this expression minus m. So as you can notice, this expression seems to be familiar with something which is in. Okay, just give me a minute. Um, okay, sorry for the disturbances. So if you look at this first expression, uh, yeah, this first expression will look um, like a differentiation, like you are calculating the differentiation of f at x naught. Okay, so this expression is similar to the expression of differentiation at x naught. Okay, or you can write this expression as this as well, x tending to x naught, and this limit as x fx minus fx naught divided by x minus x naught. Okay, so this is so if x tends to x naught, this first part is nothing but so as so if x tends to x naught, this part is nothing but f prime at x naught. Okay, yeah. So so first we prove that this is a differentiable. So first we assume that assume that am x is continuous at x naught in R. Okay, assume this fact. So what does this mean? This means that limit of x tending to x naught of amx is equal to am x naught. Now what is am x naught? So am x naught is defined to be 0. So is equal to 0. And now what is the right hand side? What is the left hand side? So left hand side, this expression, if you write, it is nothing but fx minus fx naught divided by x minus x naught minus m, okay, equal to 0, which is same to say, because m is a constant sequence, so it is constant function, so it is limit of that exists. So you can rewrite this limit expression as this. So in other words, what does this imply? Now this is f prime at x naught equal to m. Okay, so it implies that, so what does it imply? It implies that f is differentiable at x naught and f prime at x naught is equal to m. Okay, okay. So so that means if I assume, so that means if I assume that am x is continuous at x naught, then f x is differentiable at x naught. In particular, if this is continuous at x naught for some m, then f is differentiable at x naught. Now we try to prove the converse of it. Okay, so what converse? We start with the assumption that f is differentiable at x naught. Okay, um, yeah. So what will this mean? This means that limit h limit of x to x naught, f of x minus f of x naught divided by x minus x naught is this. Okay, this exists. Now you want to prove that. So for converse, so this is proven. Now we are proving converse. So we are proving the converse part. When will the converse hold? Okay, so we are looking for the converse. When will the converse part hold? So we assume that f is differentiable at x naught. Then does there exist some m in R such that am x is is continuous at x naught? Okay, okay, this is what we are trying to prove. Correct. So now, as you can see that this equation will be like am function. If I choose my m, if I so take m to be f prime of x naught, okay, then what happens? If I take this value, then from this expression, what we will get? I will get that x tending to x naught, fx minus fx naught, this minus m is equal to 0. Okay, this equal to 0. And now um this thing is what? This is nothing but limit of am at x naught, function am at x naught being equal to 0. And what is 0? 0 is nothing but the value of am at x naught. Okay, so this proves that if I assume my function to be differentiable, so this proves that if I assume my function to be differentiable at x naught, so then there exist some m. And what will that m be? That m is very specific. That m is gonna look like f prime at x naught. Okay, so there exists this m such that am is gonna be continuous. Okay, so let me write that whatever I just said. So if we assume that f is differentiable at x naught in R, then we may take m to be f prime of x naught and am, and for this m, amx is continuous at x naught. Okay, so what we have proven? We have proven. So what we have proven? We have proven this fact that if f is differentiable at x naught, so we have proven that if amx is continuous at x naught for some um, m in R, if and only if uh, fx is differentiable at x naught. Okay, now So we have proven that for some it is going to be true. So there will be m for which the function am is not gonna be continuous. Okay, even if we assume that function f is differentiable. So this m is going to be very specific. And how do we prove that? So if I go back to the options, okay, so if I go back to the options, so a first option cancels out because it removes the possibility of the converse. But we have seen that the converse is true. Okay. Uh, Similarly, option B also cancels out because it also leaves out the possibility of converse. We have shown that if I assume that am is continuous for some m, then function is going to be differentiable. Okay. Um, Now, can we differentiable at f is differentiable at x naught if and only if am is continuous at x naught for all m. Okay. So in order to say that this option is incorrect, you need to come up with a you need to come up with a m with an m such that corresponding function am will not be continuous at x naught. Okay. So yeah, and we have proven that we have proven the D part, that if I start with f is differentiable at x naught, I can find out some m for which am is going to be continuous. And if I start with assuming that am is continuous at x naught for some m, then I can prove that f is differentiable at x naught. So we have proven out this fact that am is continuous at x naught for some m, then f is differentiable, and if f is differentiable, then am is going to be continuous at x naught for some m. So we have proven this part D. Now can we say about for all m in R, uh, can we prove the continuity of am assuming that f is differentiable at x naught? Okay. So now we want to find a counter example. So we want to count. We want to find a counter example to C option. Okay. Uh, in particular, we want a function. We want to find a real m such that amx is not continuous at x naught, assuming that f is f of x is continuous at x naught. Okay, so that's the task of this thing. So as we have noticed in the previous example, in the previous solution, that if I assume that f is differentiable at x naught, then if I choose this m to be the differential of f at x naught, okay, if I take m to be this value, then I can show that am is continuous at uh, x naught. Okay, but what about if I choose a different m than this? Okay, by just tweaking a little bit. So instead of taking m to be, so instead of taking m to be f prime x, I take m to be f prime x naught plus 1. Okay, so if I take this m, so my claim is now am of x is not continuous at x naught. Okay, so how do we prove that? Again, limit of a m at x. Okay, this should, what is this value? This value is nothing but f of x minus f of x naught divided by x minus x naught minus m. Correct. Now, what is this value then? This is x going to x naught, f of x minus f of x naught divided by x minus x naught minus m. Okay, this is what we had last in the last page. So let me just calculate this part of the question. Now, what is m? M, I have chosen to be this constant plus 1. Okay. Now, if I calculate the limit of this part, okay, now I can break my limit as follows, that I calculate the limit of first part separately. Okay. And calculate the limit of the second part separately. Okay, but notice that this is a constant function. So limit of a constant function is again going to be constant, that value again. And what about this limit? This limit is nothing but f prime of x naught. This is the definition of a differential of f at x naught. And this is going to be f prime of x naught minus, sorry, plus 1. So it will be equal to plus 1. This will cancel out. It will be equal to plus 1. Now what about the left hand side? Left hand side was limit of this thing. So this limit of am, okay, amx, and that is turns out to be 1 as x tends to 0 at x tends to x naught. But in order to be continuous, it should be equal to the am at x naught. But what is am at x naught? It is 0. So 1 is not equal to 0, so it is not equal to this thing. This proves, so this implies that limit of, so this implies that a limit of am x as x tends to x naught is not equal to am x naught. Okay, uh, which implies that am x is not continuous at x naught. Okay, so what we have proven that the equivalence of am being continuous at x naught and f being differentiable at x naught uh, is not happening for all m. Okay, so if I assume that f is differentiable at x naught, okay, so it doesn't imply that am is going to be continuous at x naught for all m. You can always find out some m for which this is not going to happen. Okay, so the choice of m matters. So this will be true only for some m in the question. That's why this option C is also wrong. Okay, so now let's move on to question number 2. So I hope this question was fine with all of you. If you have any doubt, you can ask me. Okay, so now let's move on to discuss question number 2. So in question number 2, you have given you need to again find out what is true and that this statement is true or false. Okay, so a function on open interval a comma b is given, real valued function is given to be differentiable. Okay, such that f prime is bounded on ab, and the limits, basically the right hand limit, okay, this is the right hand limit of f, and the left hand limit of f at endpoint b both exist, that you need to prove. So if we assume that f is differentiable on an open interval a comma b, and its differential is bounded on a comma b, then the limits are also exist. Okay, so this is true. Okay, and we will see why it is true. We will try to prove this why it is true. So we will use mean value theorem in this proof and the differentiability. So let us discuss the solution of the question. So I will only prove one part, which is why this limit x tending to a plus the right hand limit of fx at endpoint a is this limit exists. Why does this limit exist? The right hand limit of f at endpoint a. So I will prove this part, and the second part is also similar to the argument which I will give in this proof. Okay, so in order to say that this exists, so the argument will go like this. So let me draw this first of all in the real line. How does this look like in on real line? So this is my assume that this is my real line, and this is the point a that you have, and you are approaching, and this is the point b you are having. Then this is the open interval that you are looking in, and your function is defined on this real interval, and the condition that it is bounded by some number k. It's just that at the if you take the slope, this slope is always bounded by some number. Okay, it is not going to infinity. That's what it means. So this function is not going to behave like going to infinity like this. Okay, so this will not be allowed. Correct. Infinity means the slope will be parallel to, so the infinity means the differential will be parallel to the y-axis. That is what the infinity slope is. So this is not allowed. This behavior is not allowed. So it will be like this only. Okay. And now you are approaching this point from the right hand side. Okay, that's why the a plus symbol is appearing on in the bottom of the limit. Bottom of the limit. Okay. So now my approach is, first of all, f is differentiable. So every differentiable function is continuous. So f is continuous on this open domain a comma b. First point. Second point is I will use this continuity. So in order to use this continuity, I need to prove that uh, I will use this continuity in order to say that this limit exists. And how I will use? So I will show that for a sequence, for a converging sequence, uh, converging for us for a converging sequence, for a converging sequence, uh, a plus 1 over 8 n type, which will lie on the right hand side of the interval, which will lie on a comma b. Okay, for a converging sequence like this. Okay, for a converging sequence to a, uh, the corresponding sequence, this sequence also converges. So corresponding sequence also converges. Okay, so this will be my aim to say that for a converging sequence, the sequence corresponding to the function also converges. Okay, and to show that this will converge, I will use the Cauchy criterion, which will be my third step. Criterion. Okay, so this will be my third step, and now and then I will use the continuity part to say that if a sequence converges to something, then then the limit is unique. So by continuity, it doesn't matter. Uh, so this part will be same as the limit of this sequence. Limit of this sequence f a plus 1 over n s n tends to infinity. Okay, this will be by continuity. So this will be by continuity because continuity says that the limit will be unique. Okay, so now let's we already know this fact that if a function is differentiable, uh, then a function is also continuous on the same domain. So I will start with a converging sequence. We already know that 1 a plus 1 over n is a converging sequence to a. Okay, uh, so we start with this converging sequence. Now only part that we need to show that f of a plus 1 over n is also converging, correct? And for that I'm using the Cauchy criterion. Okay, so let me quickly recall what is the Cauchy criterion. Cauchy criterion is, we say a sequence xn satisfies the Cauchy criterion or is a Cauchy sequence. We say a sequence is Cauchy if for every epsilon greater than 0 there exists n in natural number such that smaller than epsilon for all n m greater than n. Okay, yeah, so this is my Cauchy criterion. This will be I will be using. Okay, now let's uh, get down to the proof. So now we start with a sequence. So we are looking for this sequence which is a plus 1 over n. This lies in this interval and this sequence clearly converges to a as n tends to infinity. Okay, now look at this corresponding function sequence. Sorry, now corresponding look at the corresponding uh, function valued sequence. So this will be my sequence. Okay, now my claim is that this converges. So in particular, limit of this as n tends to infinity is finite. This is what this is my claim. Okay, now we use another fact which says that which is the completeness, that every Cauchy is convergent on every Cauchy sequence on R is convergent sequence on R. So that's the completeness axiom we will use. Um, so um, so for if I start with, so I'm using this fact. Let me state the fact as well. Completeness which is every Cauchy sequence on real number is convergent sequence on R. Now I will use this fact and the Cauchy criterion definition to prove this. Mm, So yeah, so let me start with for every epsilon. So let me start with some epsilon. I need to find out some natural number n. Okay, and what do I need to show? That this a plus 1 over n minus a plus 1 over m is smaller than some epsilon. Correct. Now I use something which is called mean value theorem, which says that if you have a if you have a graph like this, okay, uh, and your function derivative is bounded, which is given in our case. So in this case, assume this to be a plus 1 over n and a plus 1 over m. Okay. So in this closed domain, you can find out a point in this domain. You can find out a domain. You can find out a point. Call that point to be some c, such that c prime, such that so there exists a point c in this closed interval, such that f of a plus 1 over n minus f of a plus 1 over m is equal to f prime of c, this divided by a plus 1 over n minus a plus 1 over m, okay, which is nothing but f of a plus 1 over n minus f of a plus 1 over m being equal to f prime of c, times 1 over m minus 1 over n. Okay, so this is what you will get. Correct. So if I take the modulus as well in this, so this is mean value theorem statement. It basically says that if your function is differentiable on a closed interval, then you can find out a point in that interval whose differential, uh, you will be able to find you will if your function is differentiable on a closed interval, then there exists a point c in that interval such that the differential value of f at c will be equal to the uh, will be equal to this fraction, okay, which is nothing but you evaluate your function, which is equal to the slope of uh, which will be equal to the slope of uh, that of function on that interval. Okay, basically what do we mean by slope? That you can evaluate your function at the endpoints and you divide it by the length of the interval. Okay, so you always be able to find out such a point in that. That's what mean value theorem is. Okay, and now using this mean value theorem, I can do this. I will be able to find some c, and this will happen. So now I replace this fraction, this equation into back into my original question. So this part which is on the left hand side will be smaller than this part, f prime c times this minus this. Now we all know that f is bounded, f prime is bounded, differential is bounded, so I use that bound to make things simpler. Okay, so now we have bounded our function sequence by a known sequence that we are already know. Okay, So what does this Cauchy sequence hints you to? So this sequence hints me to 1 over n type 1 over n sequence. Okay, so I have bounded my function sequence. So I bounded my function valued sequence by a known sequence. Okay, which is already Cauchy, which is already converging, which is already Cauchy. I know. So this is nothing but 1 over n sequence for n in natural number. This is already Cauchy. So for given any epsilon, I can find out a natural number such that this entity, the entity on the right hand side, is bounded by epsilon. Okay, so I use that natural number. Okay, so let's say now since sequence 1 over n is convergent. Okay, um, so hence Cauchy. So there exists n in natural number such that this whole thing, uh, yeah, so this thing is bounded by k times, uh, yeah. So especially in particular, you can choose your epsilon to be epsilon by k. It doesn't matter. Okay. So in that case, it will be. So in that case, this f a plus 1 over n minus f a plus 1 over m. This is bounded by k times, yeah, mm, epsilon by k, which is nothing but epsilon. Okay, for all n m greater than equal to n. So this in particular implying that f a plus 1 over n sequence is Cauchy. Okay, now using the fact that using the completeness of real line, I will get that this sequence is convergent on uh, R, obviously. So this sequence is convergent, and now I use the continuity. Now I use the continuity. Now using the continuity. So in particular, what does it say? It says that as so let me just further refine the argument. So what does this last argument says? This last argument says that limit of this sequence exists. Okay, limit of this sequence exists. So now by continuity, uh, this limit, whatever limit of this function limit will be, it has to be the value. So yeah, so whatever this limit will be, this has to be equal to limit of x tending to a plus of f of a, sorry, f of x. Okay, so whatever this limit exists, this must be equal to this, because in this notation, when x is tending to a plus from the right, a from the right hand side, I'm choosing many sequences. I may choose many sequences of x. Okay, infinitely many sequences. Okay, but because this because the limit of a sequence is, yeah, so I may choose many sequences converging to a from the right hand side. Okay, and now by the continuity, this limit has to be unique. Okay, of function value sequence, and this gives you the existence, and this must be equal to this, hence this exists. Similarly, limit of x tending to b minus of fx also exists. This I leave you as an exercise. So you just need to follow the similar step. Okay, you try to prove that Cauchy criterion, that this see for a particular sequence it is convergent, and then use the continuity to say that it has to be that number. The limit is unique, so it has to be that number. So yeah, any question in that? Okay, if no question, then let's move ahead and discuss this question number 3 as well. So in this question number 3, we have given a set S where the line x equal to y is excluded, and you define a function on this set S to be this: x square plus y square divided by x minus y. Clearly, this function makes sense because x minus y denominator is not going to be 0, because you have removed that line to make sense of this function. Okay, now let us see what are the options. Now the first option is that the partial differentiation, partial derivative fx and fy both do not exist at some point. That the partial derivative of both functions exist at some point, but the functions are not continuous on it. And the third option is that both partial derivative exist and they are continuous as well. So let us see. Let us first let us calculate the partial derivative. So the function is function fx by is x square plus y square divided by x minus y on s. Correct. Now, if you differentiate it, fx, what will you get? You will get x minus y square in the denominator, 2x times x minus y minus 1 times x square plus y square, which is equal to, if you further calculate it, it is x square minus 2xy minus y square, okay, divided by x minus y whole square. Correct. Now this function, whatever you have gotten, this function on S, this function is continuous. Why? Why it is continuous? Because the denominator function, which is x minus y square, it is continuous on S. Okay, and x minus y square is non-zero on S. Number one. Second point is the numerator is also continuous. It is just the algebraic equation. It is continuous. You can further break it down that x square is continuous function, x is a continuous function, y is a continuous function, multiplication of those is a continuous function, and so on and so forth. And you can say that it is a continuous function as well. So this numerator is also continuous on S. Okay, continuous on S. And since the denominator is non-zero on S, so this fraction is also, so fraction of two continuous functions is also continuous. So this is a continuous on S. Correct. So continuous on S. Correct. Similarly, you calculate what is fy. So let us just again write this function. Okay. So what is fy? Fy is x minus y whole square. So first you differentiate x square plus, sorry, 2y minus xy minus, you keep the numerator fixed, you differentiate the denominator, you will get x 2xy minus 2y minus x plus x square, and minus plus again, it will be plus y square divided by x minus y square. So it will again be x square plus 2yx minus y square divided by x minus y square. Again, you can give me, you can take, you can give the similar argument or the same argument, because the numerator is going to be continuous, denominator is also continuous, denominator is also non-zero, so this function is continuous on S. Okay, so now let's go back to the options that we had. So first option is the partial derivative fx and fy both do not exist at some point in S. So this is untrue. Okay, both exist on all of S. Now what is the second option? Partial derivative fx and fy both exist at every point in S. Correct. But the functions are not continuous. So this is again wrong because functions are also continuous, we have seen. Only remaining option is C, which says that partial derivative exists at every point on S as well as they are continuous also. So this is correct option. So we go with it. Okay. So is this question clear? Okay. So let's move on to discuss this question number 4. In this question number 4, you have a function, a two variable function, a real valued function, such that the directional derivative of f along u at origin exist, but all unit vectors u in R2, uh, sorry. So you have given a two variable real valued function whose directional derivative exists, whose directional derivative uh, exists along u for all unit vectors u in R2 at origin. Okay. So now the claim is that so this exists for all u in R2. Okay. So now what is the claim? Claim is that f is continuous function. F is a continuous function at 0, 0. So I will give an example of a function whose directional derivative exists along all the direction at origin, but the function is not continuous at origin. Okay. So basically, I will give a counter example to this uh, question. Let me. Yeah. So the example of the question is f x y defined to be x y square divided by x square plus y to the power 4 if x is non-zero. Okay, and you define it to be 0 if uh, otherwise. Okay, so what does it mean? Simply it means that if you are on the x-axis, sorry, if you are on the y-axis, then the function is defined to be 0, and if you are on the either side of the y-axis, your function is defined to be x y square divided by x square plus y4. Okay, so now uh, the idea is very simple. You calculate the directional derivative of f in the direction of u at origin. Okay, so what is this u? This u needs to be an arbitrary u. So I'm sorry. So this u is an arbitrary direction at origin. So we take u to be, let u be a vector a comma b. Okay, so let u be a vector given by these coordinates. So now what is d a comma b f at 0, 0? This is nothing but limit. This is nothing but limit h tending to 0. Okay, uh, f 0 comma 0 plus h u. Let me write u is again. What is u? U is this only minus f 0 comma 0 divided by h. Okay, so now what is this value? This value is nothing but fa HAHB minus f of 0, 0, 0 divided by h. Correct. Now, what is HA comma HB? So you need to be a bit careful over here because if you take if your vector is in the direction of y-axis, what does it mean? It means that what are the vectors in the y direction? Let me so if this is your real axis, so in order to vector, in order to vector have a direction parallel to y-axis, its coordinate, so its second coordinate needs to be, so its first coordinate needs to be 0. Okay, so that means a needs to be 0. Okay, so what we do, we break this thing into two cases, because f takes, because look at this expression, uh, this circle. So f takes two values is, okay, depending on where the uh, point lies in the domain. So if it lies on the y-axis, it is taking 0 value. If it is, if it is lying uh, uh, except the y-axis, okay, if it is lying either side of the y-axis, then it is taking a function value. So we need to break it into two cases. So case number one, when u is parallel to y-axis, or a is equal to 0. Okay, both means the same thing, and since we are taking unit vector, so v also has to be equal to 1. Okay, 1 or minus 1, depending on the plus 1 minus 1. So depending on the direction that you are choosing, if you are taking this direction, then it is plus 1, and if you're taking this direction, sorry, it is not up to the scale I'm drawing. If you're taking this direction, then it is minus 1. Okay, so in this case, what will this expression, that expression of duf 0 0 0 gonna look like? It is limit h tending to 0, f of h, now ha is 0, so it will be 0, hb minus f 0 comma 0 divided by h. Now what is h 0 comma 0? H 0 comma 0 is 0, because it lies on the y, so it is 0. So what do we get? We get this expression f 0 comma hb minus 0 comma hb divided by h. Correct. Now what is f h comma b? Just replace, yeah. So now this value is again 0. This is also 0. Why? Because it is lying on the y axis. So this is also 0. So as a result, you get 0. So in case 1, the partial differential, sorry, the directional derivative along the vector which is parallel to y axis is 0. Now case 2, and you can also look at from the definition of function that along the y axis there is no changes happening. Okay, you are just keeping it to be constant 0. So since there is no change along the direction, so its derivative intuitively should be 0. That's what you are getting by calculation as well. Okay, now let's look at the other case when your a is not equal to 0. Okay, so in this case, if you calculate dfu 0 comma 0, which is nothing but, now now you need to replace ah and bh in this expression. Okay, in this expression you need to replace ah and bh. So ah bh square, correct, divided by ah square plus bh to the power 4 minus f00 is again going to be 0 divided by h. Okay, now let's simplify this expression. It is going to be a b h a b square h cube divided by a square h square b 4 h 4, and this multiplied by h. Now you can clearly take h square in this expression out. Okay, so taking this h square out, you get this thing, you get h cube. Now you can cancel out h cube from h cube and you apply the limit on it. So what will you get? You will get, after applying the limit as well, you get ab square divided by a square, which is going to be b square by a. Okay, so if a is non-zero, you will get b square by a type expression. So this will be your, and this makes sense because a is non-zero, so this makes sense. So this will be your directional derivative when your direction is not parallel to y-axis, and when it is parallel to y-axis, your directional derivative is equal to 0. Okay. Okay. So now what is remaining to show? So in particular, from case 1 and case 2, we can say that directional derivative of f at origin exist for all u in R2, for all unit vectors u in R2. Okay, now this exists. Now, since we are constructing a counter example, so we need to claim that f is not continuous at origin. So what do we mean by continuity of two variable function? It simply means that limit of x comma y as it tends to this origin, uh, this must be equal to this thing. This is what continuity means. Continuity of f at origin. Okay, so in order to f being discontinuous at origin, this shouldn't be, this equality shouldn't be hold. Okay, so okay, now you need to choose a specific line or a specific path to approach origin. Okay, so basically this this part, that xy tending to 0 comma 0, it may have infinitely many ways to approach origin from any part of the plane. Okay, so you can approach origin from straight lines, you can approach origin from parabolas, from ellipse, from circles which passes through origin. There are infinitely many ways to approach origin from any point in the plane R2. So we will so if this limit exists, okay, if we start with an assumption that this limit exists, then it doesn't depend on the path you choose. Okay, it is irrespective of the path you are choosing. So that's what we are going to say, that we will start with a specific path and we will show that along that path the limit doesn't exist. Okay, so so the limit uh, so the limit of xy tending to 0 0 will not exist, because if that exists, the limit exists, then it will exist along each path, it will exist along each path, and it will also be equal, okay, respective of the path you choose. So 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 we assume that that f is continuous at origin. Okay, so along any path, along any path to from along any path joining xy to 0 comma 0, the limit must exist and equal to f0 x naught comma y naught, which is 0. So this is 0, which is 0. X naught y naught is nothing but origin. This is equal to 0. Correct. So now we will contradict to this hypothesis. How do we contradict? So let us start with the parabola. Okay, consider this parabola, which is uh, x square equal to, sorry, x equal to y square. Consider this parabola. Clearly, this parabola goes through origin. Okay, this parabola goes through origin because if you graph this parabola, the graph will look like y square comma y. Okay, this will be the graph for y being a real number. This will be the graph in R2. Okay, and you can clearly see when you take y equal to 0, origin is part of this. So origin is belongs to this graph. So clearly this parabola goes through origin. Okay, now so I can choose this path also to join xy to origin. So I'm using this path. So if I calculate limit of this along this path, okay, now we calculating limit of fxy along this parabola x equal to y square. If we do that, so what we will get, this xy will become y square comma y, evaluation on y square comma y, and since it is not on the y axis, so it will be uh, x, so it will be taking the actual value of function, which is x y square divided by so on and so forth. So it will be y square times y square divided by y square of y square plus y to the power 4, and this will be y4 plus y4, which will be y4 can be taken out common, this is 2, y4 cancels out to itself, and you get half. So now let's go back to the hypothesis that we assume. So we assume that f is continuous at origin. So along any path you join xy to 0 0, the limit must exist. Okay, it is existing. Okay, but does it equal to the function value at origin? No, it's not equal, because function value at origin it's 0 0, and it is giving out you half. So it is not equal to 0. Hence, f is not continuous at origin. So in particular, I have given you a counter example of a function whose directional derivative along all the direction exists at origin, but the function is not continuous. Okay, so I have constructed out a function whose directional derivative exists at along all the directions at origin, but the function is not continuous at origin. Okay, so that's why this is a so that's why the statement that is given is false. Okay, so does this question make sense? Is it fine? Okay, so now let's move on to discuss this question number 5. So in question number 5, uh, again it's a true and false statement type question. So you have given a statement and you need to say whether it is true or false. So function is given to be two variable real valued function given such that their partial derivative exists on R2. Further, the second order partial derivative also exists on R2. Question is, does the mixed partial derivative equal for all AB in R2? Okay. So I'm not going to prove this question. I'm going to give you a counter example, and I will leave for you guys to see that why that counter example works. So first of all, let us understand what will be the counter example. Okay, what counter example function needs to satisfy. So, uh, so we will. So we need to construct a function, two variable function, real valued function. First of all, whose partial derivative exists, fx and fy exist for all AB in R2. Second of all, their mixed partial derivative, okay, also exist. The mixed partial derivative also exists for all AB in R2. Okay. Now the third part is, but they are not equal at some point. Okay. So you just only for contradiction you only need to give that at some point they are not gonna be equal. They are not equal. Okay. Okay. So this will be a counter example question. This function you need to construct whose partial derivative exists, mixed partial derivative also exists for all point in R2, but they are not equal at some point. Okay. Uh, yeah. So the example that I have in my mind is this example, and I leave it for you guys to check whether it is whether does it make sense or not. Okay. So the example goes as follow. Okay. Fxy, you define it to be x dot y dot x square minus y square divided by x square plus y square when xy is not an origin point. Okay, and you say it is 0 when x comma y is origin. Okay, so now you need to say that fx fy exist of this function, number one. Second is that their mixed partial derivative also exists. Now third point is that when you evaluate these partial derivative at origin, they aren't equal. They are not equal. Okay, so this is an exercise. I leave this for you guys to solve. Okay, and if this function doesn't work, please let me know. If this function is not that this function is not working, then we will try to construct or understand a new function. Okay, now there is a quick transition to Riemann integration. So before that, let me give you a 2 minute break for you guys, and I will be back in 2 minutes. Okay. Okay, so let's start our discussion on the Riemann integration. Okay, so this first question involves bounded variation as well. So I will skip this question first, and then I will come back to this question. Let me discuss a question which is, yeah, this is also not a nice question to start with. I'm looking for a question which is, yeah, so this is better question than the previous two questions. Yeah. Okay. So again, this is a true false uh, type question. You have given a statement. You need to say whether it is true or false. So you have given a function on a closed interval AB. Let pk be a sequence of partitions of the interval, and this pk satisfies this limit limiting condition that upper sum, okay, upper integral of f, upper sum of f with respect to pk square minus lower sum of f with respect to pkq partition, their difference, okay, and you limit it as k tends to infinity. This difference, limit of this difference is equal to 0, then f is a Riemann integrable function. That's your question. Okay. Uh, so how do we prove this? So I want you to first recall the definition of Riemann integration. Then we will go into proving these questions. So this question involves a lot of terminology. What is a partition, first of all, and then what is the U of this, L of this, and what is a Riemann integrable. So I will go one by one, and then I will prove this question to you as well. So if you have a given interval AB, okay, let's say this is an interval AB, uh, close interval AB, okay. So you partition, by partition we means, so partition P is a set of points, okay, xi's in that interval, okay. So set of finite points from in that interval, such that you pick those points. So this is, let's say, x1, this A will be x0, x1, x2, so on, xn minus 1, and then xn, okay, such that it partitions the set, okay. In particular, you can rewrite your interval AB as the union of these sub intervals, okay. So that's what a partition mean, correct? That's what a partition means. So any uh, finite subset of points from the closed interval, uh, such that, okay, so this will always be satisfied for a closed interval. So this is not a property that these points need to satisfy. These, you just pick a few points from that interval. So this is a partition. So this is partition. Okay. Number one thing. Number second thing. Riemann integral. Okay. So for Riemann integral, I need to define U and L. So if you choose a partition, so let's say I'm working with this partition P only. So you define. Uh, so now in this partition, let's say this is my function is a negative valued function. Okay, so it is like it is below the axis. Okay, so now on each of this partition, okay, so in each of the partition, your function in this particular interval, okay, x0 to x1 to x0 to x1 interval, your function attains a maximum value as well as the minimum value. Okay, so we denote the maximum of, okay, so we denote mi to be the maximum or the supremum, because it's an infinite set, supremum of fx for x sitting between xi and xi plus 1, or more or less this might be better, xi minus 1. So this is how we denote this to be this, and similarly we denote mi with small m and to be the infimum of fx, again x belonging to this subinterval. Okay, so in particular, how many intervals you have broken it into? You have broken it into n intervals and subintervals. So for each subinterval, you assign two values is mi and small mi, capital Mi, small mi. Correct. Now, what you do now? You define this third entity, which is denoted by corresponding to this partition. Okay, this partition is important because whatever you are doing, the mi's, small mi's, capital mi's, this is with respect to the partition. So this partition is important, and why this f is dependency on f is comes on, because you're doing everything with f. So that's why that's dependency of f also comes in the notation, and you define it to be the uh, yeah, you sum it up, mi, okay, times mi times the length of the interval. Okay, so it is xi minus xi minus 1, and I is varying from 1 to n. Okay, similarly you define lpf again with the minimum values to n. So in some sense, what you have done is, so let's say this is my function. Okay, this is my function, and this uh, and let's say I've taken only two partitions. Okay, just to make things less complicated. So in this x0 to x1, and this is my x2 point. So in this interval, I'm sorry for this thing. Okay, so in these three intervals, what is happening is that this is the maximum mi, and this will be the minimum. Let me note it with a different color. So uh, this will be mi, correct? And now this will be small. This will be m1, okay, and this will be m2, and this will be m2, correct? This will be m2. So now you are approximating, and what is happening? Uh, your function is sandwiched between uh, these two curves. Okay, so the first function is this m1 m2, and the second function is small m1 m2. Okay, so your function is sandwiched between these two functions, and you are calculating the and what you are doing, you are summing up. So the in LF, LP, LPF, you are calculating this area, okay, which I am drawing in this color. Okay, you are summing, you are calculating this area, correct? And in case of the UPF, you are calculating this area. Okay, and now the idea is, so this is your UPF and LPF. Okay, And there is also one more fact. Let me write that state now. So fact is, irrespective of what partition you choose, your UPF, okay. So this is fact. So let P and Q be two partitions. Be two partitions of interval a comma b. Uh, so okay. So then UPF, okay, will always be larger than LQF. Okay, irrespective of whatever partition you are choosing, the value on the left, the lower integral, the lower sum will always be smaller than the upper sum. Okay, so this we need to keep in mind. This will be important for our question. Okay, so that's why we need to keep this in mind. Or equal to, it may also possible. It may be also equal to. When you take constant like function, this will be equal in those cases, but it can't be larger than that. Okay, so now the idea is to define the Riemann integration. The idea is to smaller the partitions. Okay, you take the length of the partition to as small as you want, so that the approximation will be better. Okay, that's what you do. So this Riemann integration, uh, okay, so Riemann integration is, so you take the infimum of UPF, you call it to be the upper integral of f, and you define lower integral of f to be the supremum of L LPF. Okay, and now if these two integrals, upper integral and lower integral, are same, then you say your f is Riemann integrable on AB. Okay, this is what you say. Now there is another equivalent notion of Riemann integration which is useful to prove the Riemann integrability, which you have seen in the lectures as well. So let me state that also. So f is Riemann integrable in this interval AB if and only if for every epsilon there exists a partition P of the interval such that the UPF minus the LPF is smaller than that epsilon. Okay. Yeah. So this is an equivalent notion of Riemann integration. Okay. So we have seen the definition of the partition first. We have seen the definition of uh, lower sum and upper sum, and we have seen this fact that lower sum will always be larger than the upper sum will always be larger than the lower sum, irrespective of the partition we choose. Then we define the lower integral and upper integral. Okay. Now, and we say that the function is said to be Riemann integrable when the lower integral is equal to the upper integral. And then we state this equivalent notion of Riemann integration, which is useful to find, useful to say that the function is Riemann integrable in terms of epsilon and partition. So you say that a function is Riemann integrable if and only for every epsilon there exists a partition P of AB such that UPF minus LPF is smaller than epsilon. Okay. So with all these information, now let's try to prove this question number 8. Okay, now what does this question is saying? This question is saying that if you give me a sequence of partitions of AB, okay, let's say PK be a sequence of partition of AB, such that the limit of this limit is equal to 0, then you have to prove that f is integral. Now you may ask that this limit is being equal to 0 is the thing that you need to say to prove that Riemann integrable. Okay, so what I'm saying is this. So what we have given is this part we have given. that limit of k tending to infinity of u pk square f minus l pk cube f is equal to 0. Correct. uh, that's what is given. Now if I translate this information into the if I translate this information into uh, the epsilon definition, then what does it mean? That for every epsilon there exists k, okay, in natural number such that u pk square f minus l pk cube f, this value is smaller than epsilon for all k greater than, okay, assume this existing k to be k naught for all k greater than equal to k naught. Okay, so now you may ask, uh, now since this value in the modulus is always going to be positive because of the fact that we just saw that, so that I can remove this sign of modulus as well. Okay, now you may say that this is equal to the fact that I just stated above. So then why doesn't why it is not directly implying that f is Riemann integrable? So there's a difference. So difference is that in the above fact, for every epsilon, that is true, we are starting with any every epsilon, you need to come up with the same partition p, okay, such that this uh, UPF minus LPF is smaller than, that difference is smaller than p epsilon. But here we are having, for epsilon, I'm not having the same partition. I'm having two different partitions. Okay, so how do I get rid of this phenomena? Okay, so for that, um, so how do I make this inequality to be in terms of the single partition only? Okay, how do we do that? That is our question. Okay, so for that, um, yeah, so for epsilon by 2 greater than 0, you can find out some k naught in n such that this u pk square f minus l pk cube f, uh, this thing is smaller than um, epsilon by 2 for all k greater than k naught, greater than or equal to k naught. Correct. So now if I choose, yeah, so now take k to be k naught square, or let's say k naught, first take, let's say, square. Okay, this, call this to be k1 and k2 to be k naught cube. Clearly k1 and k2 both are larger than k naught because k naught is a real number, is a natural number. Okay, so their square and their cube must be larger than k naught. So this, in other words, this first inequality, this equation holds, okay, for both k1 and k2. So what will I get? I will get that k4 k naught 4 minus l p k k naught 6 f is smaller than epsilon by 2. Correct. And u of p k naught 6 f minus l p k naught 9 f is smaller than epsilon by 2. Okay, call this to be first equation, this to be second equation. Now sum these two equations. So what will you get? You will get UPK not 4 or 6F minus LPK not 6F, okay, plus UPK not 4F minus LPK not 9F smaller than epsilon. Now further, we know that these two quantities, this quantity is also positive, this quantity is also positive. So if I remove this, if I remove this quantity from this whole expression, the expression will be smaller. In other words, this implies that U P K naught 6F minus L P K naught 6F is smaller than or equal to, okay, this is smaller than equal to U P K naught 6F minus L P K naught 6F plus U P K naught 4F minus L P K naught 6F, correct? Which is smaller than epsilon by 2 plus epsilon by 2, which is equal to epsilon. So in other words, for epsilon greater than 0, I have found out a partition which is k naught 6. Okay, there exists a partition k naught 6 such that UPK UPK naught 6F minus LPK naught 6F is smaller than epsilon, correct? So this completes the proof. So this implies, which is equivalent to say that f is Riemann integrable on AB. Okay. Yeah. So this completes the proof of question number 8. Hence, this is true. This statement is true. Okay. So now, any questions you guys have, and we can discuss those. And the remaining questions I will discuss. I will add remaining questions in the next session, and in the next session we will also discuss a new problem as well. Okay. Yeah. Yeah. So in the next session, I will discuss problems on Riemann integration as well, and these remaining questions also. Okay. Okay. If there are no questions, so we can end our meeting over. Okay. Here.